Okay, so last time we talked about a specific instantiation of diffusion model called DDPM, and we walked through all the equations. And it was based on markup chains with Gaussian assumptions. So for the four noising steps, you start from the clean image, shrink the mean, add some Gaussian noise. That's going to be one-step noise. That's going to be t-step noise image. Just because we set it up as markup chain with Gaussian noise, Gaussian model, we can one-shot generate a t-step noise version of the image, right? And for training, we train a neural network that takes as input t-step noise image, time step t, and as the output, it tries to predict the one-step added noise on top of xt. So in order to go from xt to xt minus 1, it tries to predict the one-step noise that it has to predict to make it cleaner one step. And for sampling, you start from IID, easy to sample. So in this case, standard normal, and you follow this dynamics. So you can denoise one step at a time until you get satisfying clean image. And this, in practice, goes about 1,000 or 2,000 steps of iterations. Okay, so today, we're going to give you a bigger picture that encapsulates all the diffusion models. And then towards the end, make connection back to DDPMs. So the main question is, what is the denoising network really learning? And there are many ingredients today. But I decided to remove less important mathematical details so that I can carry the intuition first. Because I don't think it's super necessary for the scope of the class to rigorously know all the mathematical details. Because we have so many things to cover. We need to cover reinforcement learning, disentanglement, information theory, and all that. So, okay, so given a probability density P of x, definition of a score function is gradient of the log probability with respect to x. So the interpretation is the score function points in the direction where the probability density increases fastest because it's a gradient. So, for example, this picture illustrates the score function in 2D space. So wherever you are, the current score evaluated at your current x will point you to the steepest direction where the probability increases. Okay, how do we use it to generate samples from the distribution P of x? Okay, so score function points towards direction where density increases. And if we, for example, naively just follow the score deterministically, what will happen? So we start from some random location. This is step size, this is gradient direction, and that's the next iterate. And we're going to do climbing towards high density modes, right? And for multimodal density, it's going to get locked onto the nearest mode of the density function. So the pure gradient descent finds modes, and we're not going to have any diversity among the generated samples. So in other words, it doesn't really sample the full distribution. Because what we really want to do is sample according to this distribution P of x, not just sample the modes. So the logical choice would be to add noise while moving in the score direction. So that's what Langevin dynamics does. It moves towards high probability density using the score here. And second, it injects the Gaussian noise to maintain randomness. So this is the update formula for Langevin dynamics. Given your current location, it's a combination of gradient descent and adding noise. So you repeatedly apply this update, and it's going to produce samples under density P of x under suitable conditions. And so this looks nice, but the problem is, in practice, we don't have access to this function. We don't know what this is. So in score-based models, you want to replace the true score with a neural network. So neural network takes as input x and tries to estimate the score at x. So, right, so we want to replace this unknown guy with a neural network and just plug in S data here, and that's going to be our sampling function, formula. So you randomly initialize noise x0 and pass it through the score network and apply Langevin dynamics, and then if you repeat this multiple steps, you'll be able to sample from the distribution P of x. So the problem is, how do we train this score network so that it can estimate this true score? So the natural objective is what's called feature divergence. You sample x and pass it through the score network and minimize the MSE error with respect to the true score, except that we don't know what the true score is. But that's the ultimate goal of score matching. So it can be shown that minimizing the feature divergence here, this is called feature divergence, is equivalent up to a constant to minimizing trace of gradient of the score network plus 1/2 of the norm of the score network. So minimizing this objective here is same as minimizing this guy up to a constant. Let's call it double star. So what's nice about this is there's no score function inside. This is learnable. So in theory, this is useful because we got rid of the unknown term here. But this is very expensive because this is vector and this is gradient of the vector. So that's Jacobian. So it's a square matrix, and for modern image generation, this is just too much. Okay, so why is it the same? Minimizing star versus double star. Let's start from the feature divergence, and let's expand the square, this guy. So we have three terms: square of first term, square of second term, minus 2 inner product of the two terms. And first term doesn't depend on theta, so we can get rid of it. And turns out we are left with some constant plus 1/2 of the norm of the second square norm of the score network minus inner product between the score and the true gradient. So we still have this problem where this is unknown. So let's set aside the whole equation and just focus on this inner product term. That's inner product between the score network and the true score. And we're going to try to massage this equation a little bit. So gradient of the log probability, by definition of log, is gradient of px over px by property of the gradient, property of the log. Then let's expand the expectation sign. So here that's integral of x under p distribution of inner product between the score and the ratio between gradient of the density over density. And the density px cancels, so it's integral of inner product between score and the gradient. So we can rewrite the inner product in terms of coordinate wise. So I'm going to take the summation sign outside the integral. So that's sum of all the dimensions of integral of independent dimensions of individual dimensions of a score and its partial derivatives. So now let's look at this guy inside the summation. Integral of a component of the score and its partial derivative. Then I'm going to apply integration by parts. And so we started off from this equation. That's sum of integral of SI and dP di. So here, I'm just going to take it outside as expectation. So that's the expectation of x under p distribution, summation of all the dimensions of ds, di. And this expression, if you recall from calculus 1, that's exactly the divergence of S theta, the score network. And if you recall from linear algebra class, it's also the trace of the Jacobian. So the thing that gave us headache, this part here, that's equal to expectation of x under p distribution of the trace of the Jacobian. This part here. So that's why we have this double star from star. From star, we didn't have access to p of x, but double star up to a constant, that's equivalent to minimizing trace of the Jacobian plus 1/2 norm squared of the score network. So what's nice about it is this unknown true score disappeared from the equation, but practically computing this is almost infeasible for high dimensional x, because that's of size dimension of x times dimension of x. Okay, so here comes a workaround. So Hutchinson trace estimator tries to estimate this trace of Jacobian by random sampling. Okay, so first problem, we didn't have this, so we solved it, but here that's infeasible. So here, let's attack it from different angle. So for any square matrix A, expectation of random variable V sampled from standard normal distribution of V transpose AV is equal to trace of A. Okay, why? Very simple. So this guy here inside, that's scalar. So trace of a scalar is same as not taking trace. And by property of trace, you can swing things around, right? So I'm gonna reorder it by moving this guy to the right. It's A VV transpose. And I'm gonna take the trace outside. So that's equal to trace of A times expectation of VV transpose. But V is a random variable sample from that follows standard normal distribution. So that's identity, because covariance matrix of standard normal multivariable random vector is identity. So that's equal to trace of A. So for our case, maybe I should cut the proof here. Okay, I'll fix this later. Okay, so for our case, A is gradient of the score network. So trace of gradient of the score network, the Jacobian. We're going to replace it with sample V transpose, gradient of the score network, V, which can be computed efficiently because V here is just a vector. Right? All right, so slice score matching uses Hutchinson estimator, and it estimates the trace using Gaussian samples, expectation Gaussian samples, but for our purposes, it's still more theoretical. But it gives us a way to realistically implement score matching. So we used some massaging and got this equation where we got rid of the true score term, and we replaced the trace of Jacobian by replacing it with sampling. Okay, so what's the alternative? So in denoising score matching, so we are getting closer and closer to DDPMs, by the way. You intentionally corrupt the data with Gaussian noise. So given data X, you add Gaussian noise. And if let's call the corrupted data as X tilde. So the distribution of X tilde given X is going to be Gaussian distributed with mean X and variance parameter sigma squared. Just Gaussian corruption. And the goal here is to learn a score network that takes as input the corrupted X tilde and the noise level sigma, and try to sample towards the high density region of the noise data distribution. So let's try to compute the score of this known Gaussian corruption distribution. Okay, so distribution of x tilde given x is just Gaussian with mean x and noise level variance. And its log density is, by definition of Gaussian distribution, 1/2 variance squared, norm difference of x tilde and x plus some constant c. Okay, and if we take the gradient with respect to x tilde, everything vanishes except negative difference over variance squared. So this conditional score points from noisy sample x tilde back towards the clean data x. This what I mean by conditional score is this guy here. Okay, so under Gaussian corruption, the conditional score is known. We have just computed here. And we can now train a neural network to estimate this. So in denoising score matching, the objective is you sample your training data, Gaussian corrupted, let's call it x tilde, train a neural network that takes as input the corrupted x tilde and the noise level sigma, and trains with MSE target, which is the conditional score function. So this is supervised learning. So we know x, and we can sample x tilde. This is just Gaussian corruption, and target vector is analytically known. Okay, so we define the conditional distribution, just adding Gaussian noise. So what is the noisy data distribution? So Q of x tilde is, by definition, just integrating out P of x here from the joint, from the conditional. So what is the score function of the noisy data distribution Q of x tilde? So by conditional expectation, that's expectation of x under I think there's a notation difference here. That's expectation of x under Q conditional, the noisy distribution of the conditional, noisy conditional distribution, which we defined here. So what's the meaning here? So score of the noisy marginal distribution is the posterior average of conditional corruption scores. So if we train our model with the target negative x tilde minus x over sigma squared, it learns the score of the noisy marginal distribution Q of x tilde. So as a matter of fact, the score function actually estimates the score of the noisy data distribution. So we don't learn the score of the clean data distribution directly, but it learns the score of the noisy distribution at different noisy levels. So this hyperparameter sigma is going to be varied throughout the learning process. So the actual implementation version is NCSN, noise conditional score network. And NCSN learns scores at multiple noise levels. So sigma 1 is the largest, sigma 2 is second largest, etc. So you predefine a set of noise levels, and you take the weighted averaging of different scores evaluated at multiple noise levels. So here, you first sample X, you corrupt it Gaussian with Gaussian noise, and the score network takes as input the corrupted image and the current noise level, and tries to estimate the conditional score. So the authors of the paper argue why try multiple noise levels, and they argue in the paper large noise level helps global exploration, and small noise level refines the details of the image. Okay, so how do you sample this? So you start off with large noise. So this is randomly initialized. And you plug in your current image and currently large sigma. And you follow Langevin dynamics to do one-step cleaning. And you gradually decrease amount of noise to be added. So you start from pure noise, progressively refine with the lower noise score estimates. So why is it denoising? Because we trained S data with the target, this guy here. What is this guy? That's the score of the one-step corrupted image. So if we take gradient ascent along this direction, it's going to take us one step close to cleaned up image. Okay, why one step closer to clean image? Because it's gonna the gradient is gonna point along the direction where the density is higher. All right, so in the original paper, they used unit-style architecture. We discussed this last time. And they used dilated convolutions to enlarge the receptive field. And they introduced what's called conditional instance normalization to inject the noise levels. What is it? So conditional instance normalization, as opposed to just having this term here, they introduced this gamma and beta term. And gamma I here is index for the noise level sigma I. K is the feature map index. And this is going to be the learned parameters for each noise level. So for each noise level, for each feature map, they introduced this additional learning parameter, gamma and beta. And this is just an instance norm where you take xk, subtract the mean, and divide by standard deviation of the feature map. So qualitatively, it looked really, really crisp and nice. It was able to generate really high resolution images. So if we looked at the equations, it looked awful similar to DDPMs. So how do they all come together under an umbrella? So we can view DDPMs as a score learning. So let's recall the one-step noising. You start from clean image, mean shrinkage, adding Gaussian noise. That's T-step noised image. And what's the conditional score here? This just Gaussian random variable. So what we can compute the conditional score with respect to the current xt. So that's the expression here. So because we worked out for Gaussians, it's x tilde minus x divided by the variance. That's what we worked out in about 4 slides. So we're taking a shortcut here, but you can derive it yourself if you want. Okay, and this term from the forward equation, that's just this component here. So let's plug in xt minus square root of alpha t bar x0 here. And we have that the conditional score of xt is negative epsilon over square root of 1 minus alpha t bar. And what does DDPM train? DDPM trains, it takes as input the current noise image xt, noise index t, and tries to estimate the epsilon added to that noise, added to that xt. And what is the corresponding conditional score? That was negative epsilon over some constant. So looks like the corresponding score estimate is negative epsilon over this guy. So here we're going to learn this epsilon with epsilon theta. So the corresponding score estimate is this guy. So the connection is the predicting noise in DDPM is equivalent up to a scale factor this guy, to predicting the score of the noisy distribution. So DDPM is actually score-based generative modeling at many noise levels. Where in NC-SN, we predefined these noise levels before anything. But here, noise levels were defined according to these schedules. Okay, so what is the umbrella that connects everything together? So in engineering math 1, you guys have learned about ordinary differential equations, where dx is some function of x and t times dt. And in stochastic differential equation, or SDE, it adds random Brownian noise. So GT controls the noise scale, and WT is Brownian motion. So this is the added component here, introducing stochasticity in dynamics. So SDE is a continuous time version of repeatedly taking small deterministic steps. This part, plus small random noise steps. Because in ODE, everything is deterministic. If you are at some point here, you just deterministically follow this dynamics. But in SDE, you have that component, but you have this noise where you have Brownian motion. Okay, so forward diffusion can be viewed as continuous time process. This gradually transforms data into noise, and reverse time process also exists. It depends on the score function that we talked about. So I'm not going to go into much details, but the idea is if we learn the score at each noise level, then we can run the reverse stochastic process from noise back to the data. So this provides a continuous time view that unifies NC-SN with DDPM style diffusion models. Yeah, I'm not going to go too much into SDEs because that's not the prerequisite for this class. And I don't expect you to know all the details here. But derivation of NCSN and connection of the NCSN with respect to DDPM, that's all within the scope. So the unifying view is NCSN is discrete sequence of noise levels and annealed like Langevin dynamics. And DDPM is a discrete Markov chain with learned reverse Gaussian transitions. And in terms of SD view, they're all equivalent. It's continuous time forward noising and reverse denoising. So the message is pretty much all the modern diffusion models can be understood as learned reverse stochastic process guided by the score estimate. So the score estimate might be different based on which model you use, but they're going to be different only up to a constant. Only up to constant. So, okay, so that was it for pretty much all the diffusion, and these are more for the actual nitty-gritty engineering details. That's also important. So in practice, we don't want to do just sampling. We want to do conditional generation. For example, give it a text prompt and make it generate image that adheres to the given text. So this context C could be a class label. For example, draw me a picture of an elephant, or it could be sorry, here there won't be a text. So here you'll be simpler. So we'll be conditioning on discrete set of labels like elephant, car, human, etc. We can generalize it to an arbitrary text saying, draw me an elephant self-bathing itself on a mud pool, something like this. And we could also condition on low resolution image and condition on that, try to generate high resolution image. Or even give it some corrupted image and ask it to clean it. So how do we do this? We simply insert this into our model as input. So you could just turn all these guys into some embedding parameterized by some other parameter and push it inside, or just provide it as input and change the architecture here so that it can accept multiple contexts. So how do we even generalize this further so that sometimes it takes as input the condition or context, and sometimes just generates image without any condition? So we define a specific symbol for no context, and we do a guided noise prediction. So when W is 1, it's just ordinary conditional generation, and if we increase W, it tries to do stronger adherence to condition. So here it's noise network with empty context plus some mixing weight with same thing with the C the context and without context. And additionally, the diffusion steps are expensive because naively we will have to do 1,000 to 2,000 iterations per each input context. So per context, we'll have to generate a noise image and feed it to the network again and again, thousands of times, and that's going to be very, very slow. So what latent diffusion does is it introduces an encoder network to do dimensionality deduction on the input image, converts it into Z, and it runs diffusion in the latent space. So you take as input some image, you encode it, and you down project it where the dimension of z is a lot less than dimension of x. And you do diffusion about 2,000 steps in the latent space. Only after then, you pass it through some decoder that converts it back to a high resolution image. Why are we doing this? Because running repeated feedbacks in the latent space is much cheaper. Yeah, so this is basically the state of the art in image generation. And here are some examples. You can give it some corrupted image and ask it to denoise and it generates really high quality images. And you can even do colorization. You can insert these black and white grayscale images, and you can do colorization. And you can do text to image generation, where in the noise network you insert the embedding or some vector representation of the input text. And I'm pretty sure pretty much everyone has done image generation sometime in your life, right? And Stable Diffusion popularized this idea of latent diffusion for efficiency and text-to-image generation. And the high-level recipe was text conditioning, classifier-free guidance with the W parameter, and running diffusion in the latent space. And now we're starting to see realistic looking images compared to the VAEs and GANs, where we just try to do a simple image generation like digits and MNIST scale images. But here I think multiple factors came into play. One is generating, training with a lot more data. And the other is, like I said in the first lecture, giving the network enough time to self-improve. So as opposed to doing just one-shot generation, feed the output as input and repeatedly call the network itself to do one-step denoising over and over thousands of steps. So let's do a summary. So we talked about score functions, and this is not given to us. And we talked about how to work around it, and we were able to replace it with a trace of the Jacobian of the score function, but it was too expensive because it was n by n, where n is the image dimension. And we were able to replace it with Hutchinson trace estimator by sampling, and talked about NCSN, where you corrupt the image and score function outputs the score for noised image x tilde. And DDPM noise turns out noise prediction is closely related to the score prediction. It's actually the score is related to the output of the denoising network up to just a constant factor. So modern diffusion systems use conditioning, guidance, and latent space diffusion for efficiency and incorporating the user input prompts. All right, that's it for today's lecture. Thanks.